Hello, my name is Joshua Smith, and today I will be going over the topic of density. So let's get right into it. Now, what is density? Density is simply the mass of a given object divided by its volume. I'm sure all of us have heard of that. It has dimensions of mass over length cubed, and just some in general, really quickly, solids are more dense than liquids, and liquids are more dense than gases. And density is a very important concept and property to know and understand because lots of other things can be calculated from it, and lots of other properties depend on density also. So let's say you wanted to find the concentration profile of a given material over time. You'll need to know the density of it. To calculate the Reynolds number, you'll need to know the density of the fluid. To calculate the heating duty of a heat exchanger, you'll need to know the density of the fluid that's flowing within the heat exchanger. And even enthalpy and entropy, in order to calculate them, you'll need to know the density of the material because through finding density, you can calculate the mass. So there's actually three different kinds of density. There's volume density, and then linear density, and planar density. And the main difference of those three is just how you're calculating the bottom part. So for volume density, it's what we were talking about before, mass divided by volume. And unlike a microscopic view, it's the number of atoms in the unit cell times the molar mass of whatever the atom is, divided by the volume of the unit cell, divided by Avogadro's number. So this turns into grams per picometer or micrometer or nanometer, whatever. And then linear density is, actually, we'll get into that in a second. What is linear density? It is the number of atoms per unit length that are centered on a given vector. So we have to remember that it's the atoms have to be centered on the unit vector. It's very important. So here's the formula right here: number of atoms divided by the magnitude of the vector. Okay? So let's look at an example. This is a BCC structure that is beautiful, if I do say so myself, of a unit cell of chromium. Okay? And chromium has a radius of 0.1249 nanometers. And this is the vector right here that we're going to be calculating the linear density across. So it starts in the center of this atom, stops at the center of this atom. Okay? And in order to find A, we have to use some trigonometry. So we'll make this a triangle right here. And then once we do that, we find that A is equal to 4 over the square root of 3 times R. And R, we already know, is 0.1249 nanometers. So we substitute that into here, and we get a value of A being 0.2884 nanometer, or inverse nanometers, excuse me. And now we have to figure out the number of atoms that are along this line. So if we had a 3D structure, we would take spheres and we would count the number of spheres that we have. If we're trying to find the 2D structure of, or the 2D density of spherical objects, we'd have to look at the number of circles there are. But since we're only looking at one dimension, we have to look at simply the number of diameters there are along this vector. So we have one radius here, and we have another radius here. So 2 halves of a radius make one whole diameter, which means that there's one whole atom going across from here to here. Sorry, I lost my mouse there for a second. It's kind of embarrassing. So yes, the number of atoms along the vector is 1. And so the linear density is 1 atom divided by the value of the vector, which gives you 3.467 inverse nanometers. And now let's look at planar density. Planar density is, very similar to linear density. It's just instead of a line, you're looking at a plane. So it's the number of atoms in a given material that are centered on the plane. So make sure we have to keep in mind that it's the center of the atoms that lie on that plane divided by the area of that plane. Oh, easy. Number of atoms centered on the plane divided by the area of the plane. Okay, so let's look back at chromium again. We're going to find the planar density of this plane right here. So I did make the plane a lot bigger just for like visual purposes so we could see what's happening. But in reality, the actual plane value that we're going to be calculating the area of will be from the center of this atom to the center of this atom to the center of this atom to the center of this atom. So yes, so and then this is the same value of A as before. So let's just go through it. The area of this plane will be a squared, and the number of the atoms on the plane. So we got it. And so last time we found the number of diameters because we were looking at one-dimensional. Now we're looking at two-dimensional in 2 dimensions. So we have to look at the number of total circles. So if we look in this corner, we have a fourth of a circle, and we have another fourth of a circle here, and then another fourth of a circle here, and another fourth of a circle here. So 1/4 times 4 is 1. So again, we have one total atom that lies on this plane. Okay. And A again is 4 of the square root of 3 times R, and because it's chromium, just like last time, the radius is still the same. So yeah, the radius I guess you should specify is this distance here. So the R is 0.1249 nanometers. And so that means that we substitute this into here and square it, and we get 0.0832 square nanometers. So the planar density is just like before. You take one atom divided by 0.0832 nanometers, and you get 12.019 inverse square nanometers. Yeah. So why is this all important? How does this help us at all? It's a good question. There's 2 reasons that this is important to know, because of slip and directional equivalency. So slip is a type of deformation that occurs because of motion. So either compression, tension, or shear stress. Slip generally will occur along the plane with the highest planar density in the direction with the highest linear density. So let's say it again. It occurs along the plane with the highest planar density in the direction with the highest linear density. Okay, so that means that if we can calculate the linear density from this vector, and then this vector, and then this vector, and then this vector, and then this vector, and you do that for all the vectors that originate here, or here, it doesn't really matter, it's the same thing, then you will find the vector that has the highest linear density. And if you do that for all the planes again, you'll find the plane with the highest planar density. And that means that once you introduce an outside force, it is extremely likely that the slip will occur along the plane that has the highest planar density in the direction of the highest linear density. So that's kind of cool. And directional equivalency, it's kind of the same thing as this. So it means that 2 vectors that are in the same direction with the same magnitude, but have different origins, will have the same linear density for a given material. And then same thing for a plane. So if you have a plane that has the same area and has the same unit normal vector, so it's in the same direction, then those planes will have the same planar density. And then you can be able to predict that the slips will happen in those areas that have the highest planar density along the direction of the highest linear density. So that's kind of cool. Yeah, that's it. Are there any questions?